Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be discussing how Bohr's model of the atom connects with the phenomenon of atomic emission spectroscopy. Okay, so let's start with a bit of an overview of what we're going to discuss. We're going to revisit some of the features of Bohr's model of the atom. We're going to look at how that connects to the concept of the emission of light by atoms in a sample. We're then going to look at, all right, well, what's the process involved in the emission of light, and how does that then allow us to observe light of specific colors when we excite atoms of particular elements. Okay, so let's remind ourselves of the nature of Bohr's model of the atom. Okay, so here we've got a really kind of simplified sort of diagram. So we have the nucleus at the center, which is positively charged, containing protons and neutrons. We now know that the number of protons in the nucleus of the atom gives its atomic number, which is the fundamental characteristic of an element, okay, that's unique to each element. And then what we have orbiting around the outside, that in Bohr's model we have electrons in energy shells. So Rutherford proposed that all the electrons just kind of orbited around, but Bohr gave them a little bit more of a fixed characteristic, that they're orbiting in these particular places or in particular energy levels, that these energy shells increase in energy from low at the center to higher and higher energy as we move further away from the nucleus. And that these energy shells have a fixed capacity for electrons, that they can't fill an infinite number, but that number is given by the formula 2n squared, where n is the number of the electron shell. So the first shell can fit 2 electrons, and then 8 electrons in the second, and 18 in the third, and so on. Okay, and so that that we start filling up the shells based on which is the lowest available energy level, and that what we now are able to say is that each of those energy shells also has kind of little subcategories inside it, but we're not going to go into detail about that now. Okay, but so the idea is that we have these different energy shells or energy levels. So one of the fundamental ideas is that atoms in their normal state don't emit light. Okay, that if atoms are going to be made to emit light, if they become excited by absorbing extra energy from somewhere, and that tends to happen in one of 3 ways. Firstly, we would heat it, which is like when you heat up a piece of metal till it's glowing red hot. We place it with an electric discharge or electricity, or we irradiate it with electromagnetic radiation. So we shine electromagnetic radiation of a certain color or a certain wavelength on it. Okay, so now we're going to have a look at, okay, well, how does this process of emission of light actually come about? How does absorbing this energy lead to light being given off? So the first thing is that we look at this process called excitation. So we've got our negatively charged electron up here that then is absorbing extra energy from somewhere. Now this diagram is illustrating it being from a photon of light, so absorbing electromagnetic radiation, but it could be by absorbing infrared, or by thermal conductivity or whatever. Okay, but so this negatively charged electron moves from what we would say it exists in a ground state, a stable ground state, low energy state, and by absorbing this extra energy, it jumps up to an excited state. Okay, so that now that excited state exists in a different energy shell. But the idea is that this excited state, this high energy state, is fundamentally unstable. And that means then that electron will have the tendency to drop back down to its lower energy ground state, but in doing so, that it has to release or emit the extra energy that it absorbed to get there in the first place. So it gives off that energy in the form of electromagnetic radiation. So in this diagram, you're seeing it's giving off a photon of a particular wavelength. Okay, and so then it's regained its ground state, and has become more stable once more. But now the reason that this is useful or interesting for us is that the amount of energy that it absorbed to make the transition from ground to excited state will have an effect on the kind of light that it emits to drop back down. So if we look at electron A over here absorbing a particular amount of energy to go up to its excited state, it emits that same energy in the form of light to drop back down. Whereas electron B over here is the same sort of process, but we have a larger gap. And so that then when it brings it back down, that the color that's emitted by this electron will be different to electron A. And so the total energy emission that's given off here, it corresponds to the size of that gap between the ground and the excited state. The bigger the gap is, the greater the energy that's being given off, that's absorbed to go up and that's emitted to go back down. Okay, so the idea is that this energy that's emitted, when it's given off, it's detected as light that's a very specific wavelength. And when we're talking about visible light, it's light of a very specific color. Now, it could be giving off wavelengths that we can't see in the UV or the infrared, but typically we're talking about giving off colored light that we can measure using a range of different instruments. Now, what we can see is that we said just before that the size of the energy gap will dictate or will have an effect on the kind of light that's given off, the color that's given off. And we know that this is a real thing, but it's also not a random thing. That what we see is that there is a relationship between the energy and wavelength that we can have looking at these equations. Now, so what we have this equation, so links energy and wavelength, looking at the speed of light, and then this is called Planck's constant. So it's a particular physics constant which looks at the amount of energy that's involved in a photon. Okay, and so, but the essential idea here is that the energy and wavelength are inversely proportional to one another. So that as the energy increases, that the wavelength gets shorter or decreases. So that means high energy equals shorter wavelength. And then we see the opposite, that as the energy decreases or gets smaller, the wavelength gets bigger or longer. So lower energy equals longer wavelength. So what we can then say is, okay, that the size of the energy gap is going to have a direct effect on the wavelength. The bigger the energy gap, the shorter the wavelength is going to be. And so then when we see shorter wavelengths, that can tell us about the amount of energy needed, or why it's given off. Okay, but so then we kind of get to the point of saying, all right, well, if atoms can give off give off colors when these electrons can make these jumps, the idea is that for particular elements, we only see specific colors. We don't see a whole rainbow being given off. And there's a good reason for that, because remember, we're talking about electron shells exist in what we say very specific or discrete levels. Now, note the spelling of discrete here. It's the mathematical kind of definition, where it's like it's a particular amount. It's not just kind of any possible amount of energy. So they're only a discrete or specific level. And so that means that only specific amounts of energy will be absorbed or emitted. You don't have infinite possibilities. You kind of only got a certain set. So therefore, the specific amount of energy that's absorbed, we give it a name. We talk about it as quanta of energy, or a packet of energy, which is the plural of the word quantum. So each quantum of energy, each packet of energy that's absorbed and then released, is released as light of a specific color. So we've got specific energy levels, specific amounts of energy absorbed and then emitted, which corresponds to specific colors. And I recognize we've said the word specific a lot in this particular part, but the idea here is that we get, rather than an infinite rainbow, that we get a series of particular colored bands for particular elements. From memory, I believe this one is iron, but don't quote me chapter and verse on that one. So it's saying that, all right, so that we're only giving off these particular colors that corresponds to the possible jumps that the electrons can make in the energy levels of that atom. Okay, so that we see only specific colors that correspond to those gaps, and then we can look at something like this, which is called the line spectrum, and then that gives us useful information about what element it is. Okay, thanks very much for watching. Bye for now.